Now let's look at actually creating the confidence interval for these population proportions. So as you've learned about p-hat, that's what we're going to be using to estimate our population parameter p, which is a portion or proportion or percent, they all mean the same thing, of the population. This is an unbiased estimator, meaning, again, sometimes p-hat is going to be below the true population parameter about as many times as it's going to be above the population parameter, because remember, sample data often does not give us the exact population value, called sample error. The formula follows the same format that we're going to take our point estimate, in this case p-hat, subtract a margin of error, and then also add a margin of error. So we had x bar before and we have p-hat now. The only difference is the formula for the margin of error for a proportion p. And in this case, we're going to take z alpha over 2 times the square root of p-hat times q-hat, the whole thing divided by n, and notice it's all under the square root. Because you saw the z alpha over 2, hopefully that's a big hint to you that we'll be using the standard normal table. So, basically the z table. And putting our confidence interval formula together, we'll have p-hat minus the margin of error and p-hat plus the margin of error, which means it's below and above our true population proportion, assumingly. And always is the case, you want to use 5 digits to the right of the decimal if you're not entering the whole formula into your calculator at once. Okay, so let's go ahead and solve our first problem. We're told to use a p-hat of 0.40, n is 200, and the directions say create a 98% confidence interval. Answer as a percent with one place to the right of the decimal. So it doesn't tell us to create a confidence interval about a proportion, but since we have p-hat, that's kind of a giveaway. So we need to use the formula p-hat plus or minus the margin of error, which was the z alpha over 2 times the square root of p-hat times q-hat divided by n. So let's find all the parts. We'll need p-hat, which is given to be 0.40, but we might just write it as 0.4. Q-hat is 1 minus p-hat, so 1 minus 0.4 is 0.6 or 0.60. Z alpha over 2 for a 98% confidence interval, so CI to abbreviate confidence interval. This is not one of those 3 common ones, so I don't have this one memorized, and I'm going to need to work this one out. So alpha was 2%, because remember it's a complement, so 0.02 is a decimal, but I need alpha over 2, so I divide by 2 to get 0.01. And now I go to the z table, and in row negative 2.3, I find the entry 0.0102, which is too big, and then 0099, which is too small. That second one is the closer entry, so I read up, and it's under column 0.03. So even though this gives me a z-score of negative 2.33, remember, for z alpha over 2, we answer with the positive value of 2.33, and n is given to be 200. So now I'm ready to work out this whole problem. I start off with 0.4 minus 2.33 times the square root of 0.4 times 0.6 over 200, sandwich that in between my population parameter of p, and then basically copy the exact same formula all over again, except for this time I put a plus after the p-hat and before the critical value of 2.33. So to enter this into my calculator, remember you want to try to go straight across as one line. So 0.4 minus 2.33 times the square root of 0.4 times 0.6 divided by 200, and then just hit equal. I have parentheses up above in the formula because I want it for clarity's sake in reading it, but you'll notice when I enter it into the calculator, I don't need all those parentheses. When I entered the lower end into my calculator, I got 0.31929, the upper end 4807, etc. So the direction said to answer as a percent with one place to the right of the decimal. So we're looking at 31.9% to 48.1%. And of course, I always want to double check. Yeah, p hat is in that range. The 0.4 or 40% is within my confidence interval. And so we've got our answer.